A circular beam of 100 mm diameter is subjected to a shear force of 5 kilonewton. Calculate average shear stress, maximum shear stress, and shear stress at a distance of 40 mm from the neutral axis. Please read the data carefully. Try to evaluate which data which has been given to us and what we have to find out. First thing, given beam is of circular beam having a circular section and diameter clearly given to us, that is of 100 mm. Obviously, because of that, the radius is of half of that, 50 mm. Also, it is subjected to the shear force of 5 kilonewton, that is 5000 newton. Intention is to find out the average shear stress, maximum shear stress, and shear stress at a distance of 40 mm from the neutral axis. That is value of y, that is of 40 mm, which has been given to us, and intention is to find out the value of shear stress at that particular location. Now, average shear stress is given by F divided by area of circular section. F, that is the force which has been given to you, that is the 5000. Please bear us, it is 5000. Now next, area of circular section, that is pi r square or pi by 4 square, here taken as pi r square, pi into 50 square. Simplifying a very simple equation, we obtain the answer average shear stress is 0.64 megapascal. But the maximum shear stress for circular section is given by an equation 4 by 3 tau average, 4 by 3 0.64, that is of 0.85 megapascal. So you can clearly visualize that we can using a correlation between the maximum shear stress and average shear stress. Next, third one, the shear stress at a distance 40 mm from neutral axis, that is given by an equation tau is equal to f by 3I bracket r square minus y square. So please remember f by 3I, not e, but it is 3I bracket r square minus y square. F is known to us 5000 newton. 3 into pi by 4 into d raised to 4 pi by 64, sorry, pi by not 4, pi by 64 into 100 raised to 4, that is the value of I moment of inertia, bracket r square 50 square minus 40 square, and we got the value is of 0.305 megapascal, obviously, which is lesser than the maximum shear stress. Now, with this, let us proceed further with the next section, that is the I section, and intention is how the shear stress is varied along the depth of a section. Refer the figure carefully. Given I section having a two flanges, top flange and bottom flange. This two portion which is referred as flange, referred as wave. Now B is the overall width of the section. B is the overall width. You may also refer as a width of flange. D is the overall depth of section, capital D. Small b is the thickness of the wave, and small d is the depth of wave. Now, here it is clearly visualized the neutral axis, location at the centroid of the I section, and the given I section is symmetrical, it is very easy for us to find out the centroid location exactly at the center, that is small d by 2 and the small d by 2, or you may say that capital D by 2 from the top fiber and capital D by 2 from the bottom fiber, as the given section is of symmetrical section. Now, the shear stress at any section is given by tau is equal to Fa y bar by Ib. In this case, the shear stress distribution in the web and the shear stress distribution in the flange are to be calculated separately. Remember the thing which is very much important. Up till now, we have studied a simple section like circular section as well as rectangular section. Here, there will be a sudden change is there in case of I section. Just referring, this is one typical rectangular section having a huge value of width. This is another rectangular section having a large depth compared to its width. Hence, we have to find out individual shear stress value on the flange as well as on the web. So, let us found out the first shear stress distribution in the flange. Consider a section at a distance y from neutral axis in the flange. Referring the figure, this is a figure. Consider one layer in the flange at a distance y from neutral axis. So, when we consider a section or layer in the flange, then the available width for that layer is equal to the width of the flange. Be careful. So, the width of the section available is capital B, and shaded area of the flange A is equal to, that is this one. The shaded area is equal to capital B multiply by the available depth. What is this depth? This depth is nothing but d by 2 minus y, bracket d by 2 minus y, that is the depth available. So, area of the shaded portion is capital B into bracket d minus 2, d by 2 minus y. This is the equation, that is the area of the shaded area of the flange. So, distance of the CG of the shaded area from the neutral axis is given by the formula y bar is equal to y plus half bracket d minus 2 minus y. Please understood this one very carefully in the previous case. Now, if you want to understood on this tabletop, let us be understood on the tabletop. This is the given value of I section. This is the value of neutral axis. The area is over here. The CG is over here. This is known to us, that is capital D by 2. This is also known to us. Why? We want this distance, y bar. So what will be the y bar? Y bar is equal to this one, half of this distance available is d by 2 minus y. So half of d by 2 minus y. This is this distance. What is this distance? It is nothing but this one. It is distance from the centroid to the bottom fiber, this one. So if I will want to use the another color pen, it is this distance plus additional y. So if you are simplifying this, you got d by 4 minus y by 2 plus y, and VHU d by 4 plus y by 2. So VHU, if we are taking half as a common factor from both the things, y bar is equal to d by 2 plus y. And the same thing you can achieve on this PPT, that is y bar is equal to half of d by 2 plus y. Now substituting all these values on this simple equation and single equation FA y bar by IB, then F multiply by A y bar B bracket d by 2 minus y into, this is area, y bar half of d by 2 plus y divided by IB. Simplifying this equation, we got F divided by 2I bracket d by 2 square minus y square. Once again simplify, we can achieve F by 2I bracket d square by 4 minus y square. Clearly, d square by 4 minus y square. Now, hence the variation of shear stress with respect to y is of the parabolic nature. Interesting observation, because tau is equal to F over 2I bracket d square minus 4 minus y square. F is the shear force which is acting at a section that is known to us, constant value. I value for a given loading F is constant. I value for a given section I is constant. For a given section D, total depth of a section, is also constant. Variable parameter which is of y, hence it is shows of the parabolic nature. Also it is in terms of the minus sign, means it is clear that with the increase of y, shear stress goes reducing, decreasing. Now for the upper edge of the flange, that is what? Refer on the tabletop. Here, if we are referring the tabletop, at the upper edge of the flange, means this is my upper edge of the flange. Here, at the upper edge of the flange, this y is equal to d by 2, and we have to substitute this y is equal to d by 2 in the equation. Tau is equal to F over 2I bracket d square by 4 minus y square. So if we refer this particular PPT, then by replacing the y is equal to d by 2 over here, tau goes to be 0. It means that the value of shear stress is 0 on the top of the flange, while for the lower edge of the flange y is equal to small d by 2. Y value is equal to small d by 2. Please refer the figure over here on this tabletop. If I will take this as an edge over here, then my y is this one. So in that case y is equal to small d by 2. Hence, when we take y is equal to small d by 2, then tau is equal to f over 2I bracket square by 4 minus d by 2 square. And by simplifying this, we achieve tau is equal to f over 2 pi bracket d square, capital D square by 4 minus small d square by 4. 4, let us take out of the bracket, f over 8I d square minus d square, capital D square minus small d square, capital D is the total depth of the section, small d that is the depth of the web. This variation is available at the bottom of the flange. So this is number 1 equation. Now, shear stress distribution in the web. What will be the shear stress distribution available in the web? Consider a section at a distance small y from the neutral axis in the web as shown in the figure. Consider a section at distance small y. So, if you are referring a figure over here, we are taking a section or layer over here, distance y from the neutral axis. So we have to take the area of whole area of this T section, hatched area. It includes the area of flange, it includes the sum of the area of web, and we have to find out the y bar, that is the CG of this shaded area to the neutral axis. So if you are going proceed further, also refer the figure, the available width at this